This is kind of a classic problem, and I don't know, I think there's been several bets and several different pieces of money exchanged over the years because of this. It says, what is the minimum reaction time needed to catch a $100 bill if your fingers start exactly in the middle? So let's get a volunteer to come up here really quickly. We'll demo it, okay? Now this is a kind of a classic trick that you can pull on people, where I hold the dollar, well, and it should be 100, but I don't have enough money for that, so we're going for one. You have to put your fingers right in the middle, right on George's forehead, and then I'm going to drop it, and you got to catch it. You ready?
More,
so
get it more.
Okay, not quite. Let's try one more time. One more time. And usually, what you do is you say, "Hey, if you catch this, you get to keep it. If you don't, then you have to pay me $1." Right? And we're like, "Okay." And so then you drop it. And it's actually a very challenging. Thank you, sir. It's a very challenging thing to do, but guys, it's a really easy physics problem. Okay? If you look at it, and that's his thumb right there in the dollar. I measured earlier that the distance between the middle of the dollar to the edge of the dollar is 8.25 centimeters. So guys, initially, our velocity in the y direction is 0. Our acceleration in the y direction is 9.8 meters per second. Our y is 0.0825 meters, and we're going to look for our minimum reaction time. Okay? Now guys, one of the things I've done on this problem, since everything's going in one direction, I've made that the positive direction. That's okay to do if you keep all of the variables positive. So does that make sense? Acceleration is going to be downward, but I'm making that the positive direction. The distance is going to be downward, so it's positive. And guys, we could do this problem with a negative and a negative, and we get the same answer as well, as long as you keep them both going in the same direction. Okay? Really simple kinematic equation. Y equals V naught, yt plus 1/2 ayt squared. You plug in your distance, you plug in your acceleration, and you solve for the time. Okay? That is the minimum reaction time needed to be able to catch that dollar. Now, you all know that it's hard to guess when I'm going to release it, and so your eyes seeing the release and then your brain getting the signal to go to your hand, it makes it nearly impossible to catch that. Okay? And sometimes you do this trick in establishments where people's reaction time would be even further diminished, and usually their confidence would be elevated due to maybe things they've been doing at that location. Okay, but anyway, pretty simple stuff.
Playing chess.
Guys, that's just pretty straightforward kinematic equations, right? Okay, we're just taking what we've learned in kinematic equations, we're turning it vertical, we're doing gravity problems. Okay. The second example, and this example will get you status among all of your friends. You will be the smart guy or the smart gal because you will be able to answer these questions, and you'll be able to do it really easily in your head, and they'll be like, "Wow, you're amazingly smart." Cliff jumping, something that all people like, well, most people like to do, especially when there's water below you. It takes you about 2.2 seconds to hit the water when cliff jumping. How high is the cliff, and how fast will you be going when you hit the water? Okay? Super important questions. Okay? One of the things we've known, though, if you're timing 2.2 seconds, did we see human error is pretty prevalent when you're timing those things? And so you're probably going to click the thing too fast, which will basically underestimate the height of the cliff and your speed, if you will. So let's look here, guys. To solve the first one, how high is the cliff? We know V naught y is 0, ay is 9.8, made that positive again. We know the time is 2.2, so we plug into that same equation, and we come up with a distance of about 23.716 meters. Okay? Which, if we convert to feet, is about 77.81 feet. And how do I say it? That's a pretty substantial cliff to jump off of. Okay? Let's put it this way: you wouldn't want a belly flop on that one. Okay? That would hurt. Okay. All right, and just for fun, to kind of tell you the old time stories. Back in the day, the dam when I was in high school used to be about, I think, 25 or 30 feet shorter. So you know the cliffs that you guys jump off of, up there. Take that distance and add 30 feet on it. And then, yeah, we were tougher back then.
Oh.
All right, and the last thing that we're gonna look at, guys, is how fast you're going. And this is the one that all the kids want to know, and it's the easiest one to calculate. You don't even need, you just need your head. That's it. Okay. If you're looking for your final velocity, we got Vy equals V naught y plus AYT. You have 0 initial velocity, so that just drops out. And it's a really simple thing, guys. You take 9.8 meters per second times your time. Okay? Which, guys, when you're up in the hills or up at the cliff jump and you don't have your calculator, you can probably just plug in 10 there, right? And 10 times 2.2 would be around 22 meters per second. And guys, we know that, remember we did 44.7 meters per second equals about 100 miles an hour. So you can always almost double it, and I kind of calculate it for you. That's hitting the water at about 50 miles an hour, okay? Which is pretty significant. Yes?
What height is it again when you jump off and you're going so fast that water turns into basically concrete?
Well, at this point right here, if you belly flopped, it would be a lot like concrete. Because you're gonna hit and it's gonna hurt. In fact, one time a kid was jumping off the cliff out there. He came running out. We were there, and he was just like showing off and ran off. And as he went off, he got sideways, and you could see him going down. And he actually ended up breaking his ribs, and he couldn't breathe. And so we had to go in and get him out. So, yeah, when you're jumping from anywhere like those heights, you better be making sure you go in fairly vertical. So. Anyway, guys, some pretty straightforward, pretty cool, real-life applications for using kinematic equations to solve gravity problems.